Okay, if you turn to the last page of your lecture notes, that is the periodic table. Okay, so there are two main things for periodic table, right? We will always look at, okay, it is arranged according to the proton number. So the proton number is like the NRIC of the elements. Each of the element will have a unique proton number. Okay, so there are two main things that we usually look at for periodic table. The first one is actually the vertical column. The vertical column is also what we call a group. The group, okay, within the elements in the same group have the same number of valence electron. Okay, they have the same outermost electronic configuration. Okay, we will be concerned, okay, with group 1 metals and also group 17 halogen. Okay, then, okay, you can see that over here, this is the SPDF notation for the outermost shell, okay, and this is your NS1, okay, N representing the period number. Okay, so moving on to the period, if you look across the horizontal row, okay, we will be concerned with period 3. Okay, so elements like what I said, okay, the vertical columns are called groups. Okay, they have the same number of valence electron. Because they have the same number of valence electron, they react similarly. So they have similarities in their physical and chemical properties. Okay, so if I take a look at group 1 metals like lithium and sodium, you can see that, okay, it has the valence electronic configuration of 2s1. For sodium is 3s1. So generally, we say that it is actually NS1, N representing the period number. Okay. Then the horizontal rows are what we call periods. Okay, they have across the period, elements have the same number of quantum shells, or if I use a simpler word, it means that they have the same number of electron shells. Okay, but they do not have the same number of valence electron. Because they do not have the same number of valence electron, they have different physical and chemical properties. But we will be looking at the trend of this element across the period. So generally, okay, for period 3, we will be covering 3 main points. The first one is on atomic and physical property. Okay, from point 1.1 to 1.6, we have actually covered before under atomic structure and chemical bonding. We will be doing a recap. I'll be highlighting to you what you need to take note of, what you need to memorize in terms of the explanation. So please take note of it. Okay, then after that, today mainly we'll cover 2.1, which is reaction of elements with oxygen and chlorine. I'll show you some videos. Okay, we will not be doing a live demonstration because the reactions are all very reactive. Okay, so no one want to risk their life. Okay, so that is why we'll just look at videos. Okay, then after that, we'll talk about diagonal relationship with period 2 elements. So mainly there are actually group 1 and group 17. We'll be covering this point. We'll elaborate more in subsequent lectures. Okay, so for period 3, the first one, okay, I need you to really listen carefully. Okay, it may seem a little bit boring because it's explanation you have learned before, but these are all commonly tested in your H1 syllabus. So just take note of it. If you look at this sketch, you need to know how to sketch the trend of first ionization energy across the period. So the shape of this graph, you need to know how to draw. Okay, so first thing, okay, take note that over here, the general trend of first IE across the period is an increasing trend. Then you will see that there are actually 2 abnormalities. The first one being between your group 2, okay, and group 13 element. The second one is between your group 15 and 16 element. Okay, then you see how I draw the graph is that for your aluminium, it will not be lower than sodium. For your sulfur, it will not be drawn lower than your silicon. Can you just take note of this? Let me just draw this out. So to emphasize to you, you can see that the ionization energy of the sulfur is not drawn to be lower than silicon. The energy level of aluminium is not drawn lower than sodium. Can you just take note of this? Common mistake. So know how to sketch. Okay, know what to write for the y-intercept and y-axis and x-axis. If let's say I ask you, oh, how do you explain this increasing trend of first IE across the period? Do you still remember? Okay, so we need to talk about 3 main points. The first one is on nuclear charge. The second one is on shooting effect. Then I come to a conclusion based on these two, what I call effective nuclear charge. Okay, so for first IE, to explain first IE across the period, I will always use nuclear charge, shooting effect, and effective nuclear charge. Okay, how I format our answer is always the same. When I want to talk about nuclear charge, you will always have to relate to the number of protons. Number of protons increase, nuclear charge increase. I want to talk about shooting effect, you always have to talk about the electrons in your electron shells. So successive electrons added to the same outermost shell, shooting effect remains the same. When shooting effect remains the same, nuclear charge increase, okay, your effective nuclear charge, which is a sum of your nuclear charge and your shooting effect, will increase. When your effective nuclear charge increase, the attraction between the nucleus and the outermost electron, take note that I'm using the term outermost electron, not outermost shell. Because by definition, okay, your first IE is to remove 1 mole of electron. So take note, I'm talking about attraction between the nucleus and outermost electron. Then you conclude with more energy is needed to remove the outermost electron. Can? Okay, so you need to know this explanation by heart. Okay, don't try to use your own words because you tend to miss out keywords. Okay, so please make sure you know how to give this explanation. Okay, then the next part is to explain the abnormally. The first one is between, for first IE, okay, is between your group 2 and group 13 element. Okay, generally, okay, if you look at if it has an electronic configuration of NS2 and NP1, okay, as compared to NS2, okay, in this case, I have to compare between aluminium and magnesium. Okay, you can see that less energy is needed to remove the 3p electron, okay, from Al as it experience increased shielding from the filled 3s subshell. If I look at Al, you can see that for Al there is an extra 3s2 or 3s2 subshell. Okay, the keyword here is that I'm talking about subshell. I refer to filled 3s subshell. Okay, 2 things, okay, you need to take note of. The first is that you need to recognize that I am supposed to write down the electronic configuration. When you explain abnormally, okay, or the exceptions to your first ionization energy, you must include the electronic configuration, the SPDF notation. Then the second thing, I will talk about less energy needed to remove the 3p electron because of increased shielding from the filled 3s subshell. Okay, so you need to know this explanation by heart as well. Okay, next one. Exception, again. Okay, if you are comparing between the electronic configuration of NS2, MP3 as compared to NS2, MP4, okay, then I need to know that less energy is needed to remove the paired 3px electron in sulfur. It experiences inter-electronic repulsion. Why is there inter-electronic repulsion? Because you see that there are 2 electrons occupying the same 3px orbital. I am using the term 3px orbital. Okay, this inter-electronic repulsion is when the 2 electrons occupy the same orbital. Do not use the word subshell because, okay, in your subshell, in your 3p subshell, it actually contains your 3px, 3py, and 3pz orbitals. This inter-electronic repulsion is arise because of 2 electrons occupying the same orbital, not subshell. Please take note of the difference between these two. Okay? So here, okay, in order for me to show the inter-electronic repulsion, okay, of 2 electrons occupying the same orbital, you need to give your SPDF notation, and in particular, you need to show the orbitals. Okay, so you need to write 3px, 3py, 3pz. Just a quick recap, just take note that it is a 3, p, then your x is a subscript, the number of electron is a superscript. This is how you represent, okay, the individual orbitals. Okay, so take note of how to represent the individual orbitals. Any question? I don't think there is, so let's just move on. Okay, so just a quick summary. Okay, for us to explain the trend of IE for the exceptions, meaning to say between my group 2 and group 13, and then group 15 and 16, this is only for my first ionization energy. Okay, when I want to talk about exceptions, then you need to talk about first, state the electronic configuration. Usually 1 mark will be given for electronic configuration. Okay, so please make sure you give the electronic configuration. And in particular, if you mention inter-electronic repulsion, please make sure that you show in terms of the 3px, 3py, 3pz orbitals when you write the electronic configuration. So take note. Okay, then I will start off with less energy is required to remove. Okay, so this is the sentence that I will try to memorize to start off the explanation. The last thing is to provide the reason, be it whether is it increased shielding, okay, by field subshell or inter-electronic repulsion. Okay, this is one way for you to remember how to explain the two abnormalities across the period for first ionization energy. Okay, so take note of this. The next thing that I need to be able to explain is the atomic radius. Now, sometimes the question, what they do is that they will give you a sketch like that without indicating the proton number, without indicating the identity of the element. So you are expected to guess whether, if let's say for example, this point that I highlighted in yellow, you are supposed to deduce whether is it magnesium or not. Okay, this is one way that they can ask the question. So that is why you need to be able to sketch out the trend of your first IE, and in this case, your atomic radius. Okay, it is the same old story again. Because you need to talk about the nuclear charge, you need to talk about the shielding effect, you need to talk about the effective nuclear charge. Okay, so when I compare from sodium to chlorine, for my atomic radii, you can see that the number of proton increase, nuclear charge increase. Same thing, nothing new. Successive electron added to the same outermost shell, shielding effect remains the same. Same thing again, when I compare nuclear charge and shielding effect, because shielding effect remains the same, nuclear charge increases, so the effective nuclear charge increase. But now there is a difference between this explanation and the explanation for first IE, is that instead of saying the outermost electron, I say the outermost shell. Because I'm talking about the radius, so I'll be using the term outermost shell is attracted more closely towards the nucleus, atomic radius decreases across the period. Okay, so this explanation is exactly the same as the explanation to explain why first IE increases across the period. The only difference is that I talk about the outermost shell for atomic radius. Okay, some of your eyelids seems to be closing. Okay, am I that boring? Okay, if you are tired, please stand up. Okay, and then go and wake yourself up. Now, the next part is on ionic radius. Ionic radius, there are a few trends I need to take note of. You look at this particular sketch. The first trend that I can take note of is, of course, you can see that for the same isoelectronic series. So what is isoelectronic series? I say that Na+, Mg2+, Al3+, Si4+, they are in the same isoelectronic series, meaning to say they have the same number of electrons. You go and count sodium ion, Mg2+ ion, they all have 10 electrons. For P3+, S2-, Cl-, they are also in the same isoelectronic series, meaning to say that they have the same number of electrons. Total number 18 electrons. So within the same isoelectronic series, you can see that the trend of ionic radius decreases. Then The other trend, very obvious, you can see that your anion will have a larger ionic radius than your cation, right? Anything else that you can observe from this sketch? Okay, then you may want to consider the next thing is that if I compare your sodium ion with your sodium, which of it will have a larger radius? If I compare chlorine, okay, atom with a chloride ion, which of it will have a larger radius? Okay, think. Now, first thing, let's look at this sketch. Okay, we say that the ionic radius decreases for ions with the same isoelectronic configuration. Now, it is the same old story again. Okay, nuclear charge, shielding effect, and effective nuclear charge. Okay, so nuclear charge, same thing. I talked about the proton number increasing. Then you talk about the shielding effect. Then you talk about the shielding effect being exactly the same because they're isoelectronic. They have the same number of electrons, meaning to say they have the same number of electron shells. That is why shielding effect remains the same. Effective nuclear charge, okay, will increase. Hence, the outermost shell, take note, okay, here because I'm also talking about the radius, so you are using the term outermost shell, is attracted more closely towards the nucleus. The ionic radius decreases across the isoelectronic series. Okay, so take note of this. So you can see that the general trend, okay, of the explanation for first ionization energy, for atomic radius, and for ionic radius is all the same. I discussed nuclear charge, shielding effect, effective nuclear charge. Okay, these are the three things that I always discuss when I talk about the trend across the period for first IE, atomic radius, and ionic radius. Then, okay, when I compare anions, okay, are larger than cations, I think this is quite obvious. You look at the number of shells of electron. Okay, for anions, if I compare sodium ion with my phosphorus ion, you can see that for the phosphorus ion, there is one more electronic shell. Okay, because of this, that is why your anions tend to be larger than cation. Okay, and then if I compare between cations and the respective atoms, for example, sodium as compared to your sodium metal, okay, what happens is that for your sodium metal, it has one more electron shell, okay, 3s1. Okay, because when you form the sodium ion, it has lost the electron, the electron from the 3s orbital. Okay, so that is why over here with one more shell of electron, that is why your cations tend to have a smaller radius as compared to the atom. Anions, okay, what happens is that now for anions, it gains electron to form the anion. It will have more electrons than protons. When you have more electrons than proton, the net attractive force for the valence electron by the nucleus will decrease. What do I mean by that? If I have chloride containing 7 protons and 18 electrons, as compared to a chlorine atom containing 17 protons and 17 electrons, now you have one more electron. Okay, so now you need to split the attraction between 18 electrons as compared to 17 electrons. So the net attractive force would be lower. Because of that, okay, that is why anions will have a larger radius. Do you understand? Okay, so take note of this trend. Any questions so far? Okay, so all in all, right, if I want to summarize this, when I want to explain the trend in the radius, okay, we usually examine first the number of electron shell, then I talk about the effective nuclear charge. Okay, if the number of electron shells is the same, then I'll discuss effective nuclear charge. Okay, Ken? Okay, as I go through, okay, try to read through it again, okay, and then try to internalize the explanation and the trend. I mean, these all have been covered before, okay, but why are we emphasizing this again is because they are commonly tested. Okay, so try to keep your eyes open. Okay, Ken? Now, melting point. Okay. Okay, the next person who sleep, right, I will pass the mic to you. Then you explain for us the melting point. Okay, I mean you learned this before, right? So it makes sense for you to be able to explain. Okay? Can I? Okay. Now, melting point. Okay, general trend for melting point is that, okay, for usually when you explain physical properties like melting point, boiling point, solubility, we always look at what? Soft boiled pigeon egg. Structure, bonding, particles, and energy. So it is the same format of answers that we'll look at in this case when you want to explain the trend. Okay, so generally, sodium, magnesium, and aluminium, they are all having giant metallic structure. With the giant metallic structure, okay, the bonding is that it consists of strong metallic bonds. The particles is that it is of cations and a sea of delocalized valence electron. Okay, a lot of energy is needed to break the strong metallic bond. So typically for your metals, it tends to have higher melting point. Okay, but if I want to compare the trend, okay, across from sodium to aluminium, okay, it will increase from sodium to aluminium. Why? Because if I look at metallic bonds, if I want to compare the strength of metallic bonds, you have to look at the electrostatic attraction between the cations and the sea of delocalized valence electron. When you have more number of delocalized valence electron in the case of aluminium to form Al3+, lose 3 moles of electron, then you can see that the electrostatic attraction would be stronger. As a result, we say that the strength of metallic bond increases. So that is why the trend of melting point is increasing from sodium to aluminium. Is that clear? Okay, so the first thing is that you always have to state what is the structure, bonding, and particles, which is a giant metallic structure, okay, consisting of cations and sea of delocalized valence electron held together by strong metallic bonds. Take note, I'm using the term sea of delocalized valence electron. Okay, keywords like this, don't anyhow use your own words. Take note. Then, okay, the special case is for silicon. Silicon has the highest melting point across period 3. Why? Because it has giant molecular structure, okay, and this giant molecular structure is consisting of silicon atoms held together by strong covalent bond. Okay, so a lot of energy is needed to break this strong covalent bond. So that is why silicon has one of the highest melting point across period 3. Okay, so that is how I explain the trend, okay, from sodium to aluminium. Then I talk about silicon. Then when I look at phosphorus, sulfur, chlorine, and argon, okay, I need to recognize what is the structure for phosphorus, sulfur, chlorine, and argon. Okay, they are actually made up of simple molecular structure, okay, consisting of P4, S8, and Cl2 molecules or Ar atoms. Here I want to highlight to you, okay, that your phosphorus, okay, under room conditions will exist as a P4 molecule, sulfur as a S8 molecule, chlorine as a Cl2 molecules. Okay, this is something new to you, okay, so you may want to take note of it. They are simple molecular structure, so when we want to discuss melting point, we cannot look at intramolecular bond, we have to look at intermolecular forces of attraction. Okay, so the intermolecular forces of attraction that I will be comparing is the instantaneous dipole-induced dipole interaction. Okay, because they have very different MR, so I will be discussing the ID-ID interaction. Okay, so from here, right, can you make a guess which one of it will have a higher melting point? You look at the size of electron cloud, the one with a higher MR will have the stronger ID-ID interaction. Okay, so here, this is the general trend. This trend you need to know by heart. Argon has the lowest melting point. okay, followed by chlorine molecule. The one with the highest melting point would be S8. Okay, because the size of electron cloud increases, larger electron cloud more easily polarized or more polarizable. Take note of this term, often missed out in your explanation to compare the strength of your ID-ID interaction. More easily polarized, so that is why the strength of ID-ID interaction increases. Okay, so can you just put an asterisk for this to describe it to become more easily polarized? Take note. Can? Okay. So to explain the difference in melting point and boiling point, okay, take note that some of you I cannot see whether you are sleeping or not because your eyes are very small. Okay, so can you open your eyes bigger and look at the screen? I mean, there's nothing wrong. Okay, just yeah. So take note. Okay, to explain the difference in melting points and boiling points, okay, I first have to explain the structure, bonding, and particles. I told you. Okay, this is the same old shit that you need to know. Okay, please make sure that you know that you need to state structure, bonding, and particles. Okay, then the next thing is that you compare the strength of the different bond. If you all have a giant metallic structure, then you compare the strength of the metallic bond. You look at the number of delocalized valence electron, right? Okay, if I want to talk about IMF, in particular instantaneous dipole-induced dipole interaction, then you compare the size of electron cloud. How easily polarized is it? Okay. So take note of the factors. Okay, if you are not sure, please refer back to your chemical bonding lecture notes. They are all inside. Then you conclude with the egg, which is energy. You talk about whether more or less energy is needed to break the stronger or weaker bond. Okay, so this format of answer we have been telling you, okay, since chemical bonding. Okay, so please make sure whenever you have a melting point, boiling point question, follow this format of answer. Okay, all the points would be included in your answer. Okay, so take note. Okay, electrical conductivity. Okay, for electrical conductivity, this is the trend. I think it is quite easy to understand that for metals like sodium, magnesium, and aluminium, they will conduct electricity. Silicon, it is what we call a semiconductor. So that is why, okay, it has some form of electrical conductivity. Okay, and then those that are of simple molecular structure like phosphorus, sulfur, chlorine, and argon are non-conductor of electricity. Main thing I need to know about electrical conductivity is whether there is mobile charge carrier. Keyword, mobile charge carrier. Keyword, mobile charge carrier. So you need to include this in your answer, mobile charge carrier for electrical conductivity. Mobile charge carrier. Take note. If I have sodium, magnesium, and aluminium, can you see that they have delocalized valence electron? This delocalized valence electron will act as mobile charge carrier. Okay, so please take note, you need to include mobile charge carrier in your answer. Then you see that, okay, you don't laugh. Okay, I mentioned more than 7 times, I remember it, and you don't, because it's always not in your answer. Okay, so conductivity of metals increases from sodium, magnesium, and aluminium. Why? Because you have increasing number of delocalized valence electron. Okay, aluminium can contribute, okay, to form 3 electrons, right? Okay, 3 moles of electron because we form Al3+. These 3 electrons, 3 moles of electron can act as a mobile charge carrier. Whereas for silicon, it is a special case that you need to know. It is a semiconductor. We will not be talking too much about it, but I just need you to know that it has some form of conductivity because it is a semiconductor. Okay? If you are interested, just take material science, okay, in uni. Okay? Next thing is that for phosphorus, sulfur, and chlorine, there's 0 conductivity. Generally, simple molecular structure will have 0 conductivity, okay, because they do not, okay, their valence electron are localized in a covalent bond. So that is why they do not have mobile electrons or mobile ions to act as mobile charge carrier. Okay? So generally, to explain conductivity, you need to first be able to identify the mobile charge carrier. Okay, so example of mobile charge carrier in the form of in your giant metallic structure or in plane of graphite it is actually delocalized mobile valence electron. For your ionic compounds, it is generally mobile ions. Just take note that for ionic compounds, it needs to be either in aqueous solution or in molten state. Ionic compounds do not conduct electricity in solid state. Okay, so that is just a recap. The special case we talk about is silicon. So just take note that it is a semiconductor. It has some form of electrical conductivity. Can? Okay, next one, electronegativity. Electronegativity is we have mentioned this in chemical bonding as well. So what happens is that, okay, how do I remember the trend? Very simple. Okay, if you turn to the last page of your lecture notes, okay, which is the periodic table, there's only one thing I need to memorize. The one thing I need to memorize is that in your syllabus, okay, the most electronegative atom is fluorine. So across the period, electronegativity will increase. Down the group, it will decrease. Okay, so that is the only thing I need you to remember for electronegativity. Okay, fluorine, most electronegative. So from there, I can see the trend already. Across the period, okay, you will see that electronegativity decrease. Down the group, across the period, electronegativity increase. Down the group, it decreases. Okay, so take note of that. So over here, okay, explanation, okay, is that you need to recognize that the effective nuclear charge increases across the period. Okay, so that is why the electronegativity increases across the period. Okay, so generally, okay, some things for you to take note of, some important trends is that hydrogen is the least electronegative non-metal element. And then there are three most electronegative elements that you need to take note, which is nitrogen, oxygen, and fluorine. Full of nonsense. Okay, so just remember that. Fluorine, oxygen, and nitrogen, okay, usually they are able to form hydrogen bonds, okay, due to a larger partial positive and negative charge that is present. Okay, not too difficult. Okay, so next thing, okay, a quick summary of whatever that we covered. Okay, can you quickly just take note whether is it increase or decrease? I.e., across the period, increase. Atomic radius, decrease. Ionic radius, decrease. For ionic ionization energy, atomic radius, ionic radius, you'll be using nuclear charge, shielding effect, and also effective nuclear charge. Melting point, okay, from sodium to silicon increase, okay, then the general trend for P to AR is decrease, but take note that for, okay, the melting point, okay, the one with the highest melting point is actually sulfur because the molecular formula is S8. Phosphorus is P4. Okay, so chlorine is Cl2. You just need to take note of this. Then you can go and look at the MR. The one with the larger MR will have a higher melting point because it has a stronger ID-ID interaction between molecules. Electrical conductivity increases from sodium to aluminium. Silicon, special case, semiconductor. Then the rest of simple molecules do not conduct electricity. Electronegativity, just remember that fluorine is the most electronegative atom. So that is why electronegativity increases across the period. Right? All memorized already? Okay, so with this, can you quickly solve, okay, the question, examples on page 10? Okay, Ken? Now, Sana. So, what could X be? So, for this trend, okay, you can see that there's a slight decrease from X to X plus 1. Okay, so this is the slight decrease that we are talking about. So, you know that for the general trend across the period, there should be 2 slight decrease. Okay, so this should be the first slight decrease. So I can guess that X will have a NS2 configuration. It should be from group 2. So that is why X is magnesium. Are you able to get magnesium? Ken? I think most of you are able to get, right? There shouldn't be any issue. Now, okay, over here, okay, it's just an extension question. If the graph shows second ionization energy, what happens is that, okay, the electron is actually removed from an X plus. Okay, so effectively your X would be aluminium. Okay, you can shift that the graph will actually shift to the right. So that is why your X will be aluminium if it is a second IE. Okay, so I don't want to focus too much on this because your syllabus is usually for first IE. Now, over here, okay, the answer, okay, is, sorry, is D, not C. The answer is D. Okay. Over here, what happens is that, okay, this explanation, don't be too worried. Later on, I'll send through your chem rep, then they will send it to you. So just listen to what I have to say. Okay. Now, first thing, okay, if I compare Ca2 plus as Mg2 plus, right, it is down the group. Okay, down the group, the general trend, okay, we have not talked about this, but, okay, common sense, okay, I shouldn't use this word in case you get it wrong. Okay, so down the group, okay, ionic radius will actually increase, okay, because you can see that, okay, it will become, the electron cloud will actually get larger. So Ca2 plus will be larger than Mg2 plus because Ca2 plus is further down the group. Okay, S2 minus and S, N ions have larger radius than their respective atom. This is what we covered, okay, because it has one more electron shell. Okay, so that is why it is larger. So that is why option B is out as well. Option C, okay, both your neon and magnesium 2 plus have the same number of electrons. Okay, the shielding effect is approximately the same. Because they only have 10 electrons, the shielding effect is approximately the same. But Mg2 plus has more number of protons. That is why it have a higher nuclear charge. Nuclear charge higher, shielding effect almost the same. It will have a higher effective nuclear charge. Okay, outermost electron, okay, is more attracted closely towards the nucleus. So that is why, okay, your Mg2 plus will have a smaller ionic radius. Okay, so the atomic radius of neon would be larger than that of Mg2 plus. You see that when I explain, right, okay, I am using the same concept. I talk about the nuclear charge. I talk about the shielding effect. Then I compare the effective nuclear charge. Okay, nothing new. Okay, take around 20 seconds to read through this. Okay, try to understand the explanation. No need to copy down. I will send to your chem reps. Okay, option D is obviously the answer because we learned that across the period, atomic radius decreases. You need to be able to explain. So when you are in the train, you have nothing to do. Okay, just talk to yourself and explain. No, you talk about the nuclear charge, you talk about the shielding effect, you talk about the effective nuclear charge. Okay, if someone asks you why you're talking to yourself, because you just ask them to keep quiet, you are trying to recall for trend across the period for period 3. Okay, Ken, take note of this. Now, so far, okay, we have covered the atomic and physical properties. Okay, I'm going to move on to the last part using the last 10 minutes to show you the reaction of the elements with oxygen and chlorine. So, okay, basically, it's all in your lecture notes. I'm just going to highlight to you, okay, what you need to know. Okay, listen. You can see that there are 2 parts of this. The first part is the equation. Okay, there are 2 things I need you to know for the individual elements, be it reacting with oxygen or reacting with your chlorine. First thing, you need to tell me what is the color of the flame. Okay, it has been tested before, has been asked before, so you need to be able to memorize. If sodium burns in oxygen, it will give an intense yellow color flame. Then you need to be able to write out the equation. These are the two main things I need you to know from this table. There are a lot of things for you to memorize. Okay, please make sure that you go back, look through it again, and then try to memorize it. Okay, I'm going to show you what happens so that it leaves a deeper impression on you. If I burn sodium in your oxygen, this is what is going to happen. Okay, so this is sodium reacting. This is your sodium. Okay, I'm heating it up. This would be the intense yellow flame. Okay, then what is left behind will actually be your white ionic solid of sodium oxide. Okay, now if I look at magnesium, it is a bright white flame, white ionic solid. Okay, so this is how it looks like. Okay, this is a magnesium strip. Okay, that they are going to insert it in. Okay, this is containing oxygen inside. It's very bright. Okay, so that is your bright white flame. Really very bright. Okay, so you need to memorize this color. Bright white flame. Magnesium react with oxygen to form magnesium oxide, a white solid. Then the next one is aluminium. Aluminium, okay, what happens is that at the start you'll have a reaction, but after that the reaction will tend to slow down because it will form your aluminium oxide, which is what you learn in O levels is quite unreactive. Okay, so let me show you. Okay, oxygen gas is inside. This is your aluminium. Okay, metals are usually gray in color. So that is the aluminium powder. Whoa. So it actually blew a hole in the... Okay? So do not try this at home. Can? Okay, so take note. I need to know that it will form Al2O3, a white ionic solid. Okay. Now the next one is silicon. Okay, silicon. Over here, take note that there's no reaction at room temperature. Only when you do it under strong heating, okay, then there will be a reaction with oxygen to form your silicon dioxide. Okay, let's see what happens. Fast forward. Fast forward. Oxygen gas is actually channeled in. Okay. So the main thing I need you to know from here is that silicon dioxide will be formed. SiO2 is formed when you react silicon with oxygen. Okay. Next one. Okay. Phosphorus, pale bluish green flame. Later the video, right, you cannot really see that it's pale bluish green. Okay, but I'm still going to show it to you. Okay. Over here, oxygen with phosphorus. White phosphorus. Okay, so take note, okay, that you need to know that it is a pale bluish green flame. It doesn't look like it, but it's actually pale bluish green flame. Okay, then the equation is, the main thing I need you to know is the second equation. Okay, P4 solid, you need to know the state symbol reacting with oxygen to form P4O10 solid. Okay, please take note of the state symbol, everybody. Okay, the product form are all in solid state. Okay, when it reacts with oxygen. Only for sulfur, then it will form, okay, your SO2. Then it will be oxidized to form SO3. Okay, so what happens for oxygen with sulfur? okay, they tell you that it's a pale blue flame. Okay, let me just fast forward. This is your sulfur, yellow in color. Can you see this pale blue flame? You can actually see this, right? If you have been to Indonesia before, to a mountain called Ijen, okay, you can actually trek down the mountain, okay, in the middle of the night, okay, then you will see that this blue flame. Next time, okay, when you have the chance, okay, you can go to this place, okay, in Surabaya, okay, it's actually this Ijen. Okay, you will be able to see why is it that it is this blue flame is because of the presence of sulfur reacting with oxygen in the air. Okay, this is real, this is not fake. So yeah, so just take note. Okay, so if you go there and then people is asking, hey, why it burns blue flame, then you tell them S reacting with O2 to form SO2, so you will see a pale blue flame. And then you can see that it's actually quite smelly because there's sulfur. Okay, and then the sulfur, you can see the workers carrying the sulfur, the yellow solids up to sell. Okay, it's just a few cents. Okay, now the next thing is I'm going to show you very quickly. Okay, I don't have much time. Okay, I'm going to show you the one for chlorine. Now, first thing, okay, chlorine with sodium. Okay, bright orange flame. Okay, then take note that it will form a sodium chloride. Okay, chlorine gas is usually yellowish green. Okay, then after that you will see that I insert in my sodium in. Do not try this at home. Chlorine reacting with sodium. Okay? Can? Okay, so you will form your sodium chloride solid. Take note, it is sodium chloride solid. You need to include the state symbol. Okay, move on. Okay, next thing, okay, magnesium, okay, with chlorine. Just fast forward this. This magnesium strip, okay, you can see a bit green, yellow, that is your chlorine gas. This is no superpower, this is chemistry, okay? What happens, okay, let me show you again. Slow motion. It's like a thunderstorm. Okay, take note, okay, the color is a bright white flame. Can you see it's white? Yes, right? So you will form a solid magnesium chloride. Take note, solid magnesium chloride. Okay, so what is happening is that, okay, the powder actually reacts very aggressively in a series of small explosions. Next, aluminium. Okay, aluminium, okay, mainly, okay, can you see this aluminium is reacted away? This strip is actually aluminium, like your aluminium foil. Okay, then it will actually form, okay, dimerize to form Al2Cl6. This Al2Cl6, right, if I cool it down to room temperature, you can see that it actually forms a pale yellow covalent solid. This pale yellow covalent solid is a solid of the aluminum chloride. Okay, so please take note. Next, with silicon, okay, the second last one. Okay, not so much of a reaction, react slowly on heating. Okay, but if let's say I cool it down, okay, I cool it down to room temperature, what will be formed, okay, is actually a, why so slow? SiCl4 in liquid state. Okay, so just take note, okay, you can see that reaction of chlorine with sodium, magnesium and aluminium will form solid, okay, as the product. But for SiCl4, for silicon, the product form is actually a liquid. Can you take note of that? Okay, last one with phosphorus. Okay. Okay, phosphorus, it will form a solid of your PCl5. Okay, so once I cool it down to room temperature, it will form a solid. Alright, Ken? So go back, okay, read through this table again, and then know how to balance the equation and also give the color of the flame. That's all for today.